Would you please make welcome for talk number 2 in a series of 2, Professor Iver Cairns.
What I want to focus on is space weather, and what you have showing here is the sun seen in extreme ultraviolet light from Solar Dynamics Observatory in the States. It's a time-lapse movie going from 2010 to 2020, and you can see activity and variations everywhere you look on the sun. So for instance, you notice these bright regions here. Those are regions that are hot and have strong magnetic fields. They're not constant in time. They instead are varying, they're flickering all the time. What does that flickering mean? It means changes, it means heating, acceleration of particles. It means things that might be thrown off from the sun into the solar wind, moving towards the Earth. And space weather is all about solar activity that influences the Earth. And if the sun is like this, we should expect to see significant variations of at least the ionosphere, the ionized portion of our atmosphere, and the region around the Earth, driven by the sun. And that's what I will try to talk to you about today. So let's just stop that. Okay, so we're going to be looking at a situation like this. We're looking at the sun driving activity towards the Earth and elsewhere in our solar system. And we'll be interested, for instance, in the magnetic field and around planets, and in particular, our Earth. And so this is a display for the Earth here. The night side, of course, is dark, front side lit. We have the magnetic field lines here. What you're perhaps expecting is a nice dipolar field that looks symmetric on both sides, with the field lines coming out from the South Pole, going up to the North Pole, if you're looking at Earth. And you'll notice that it's not symmetric. You'll notice that there's a region here, so-called cleft or cusp, another one on the south side here, which looks like it's sort of open, perhaps, towards material from the sun coming in here, maybe following magnetic field lines down towards the Earth, down towards the auroral zone and the polar caps around the Earth. And that's one way in which space weather will occur. Another way is perhaps much more direct. We just saw the extreme ultraviolet light and the X-rays. That light has enough energy to be able to do multiple things for atoms. It can ionize the atoms, it can heat them. So the ionized material can then interact with the magnetic field, be subject to electric fields. So if you have a time-varying magnetic field, you might know that you get an electric field, just like a dynamo on some people's bikes, for instance, driving the light on their bike. Those electric fields can then move the plasma around, accelerate it, change things. And we're going to be looking at those two forms of activity. One is basically driven on the front side of the Earth here, due to X-rays and extreme ultraviolet light coming out and hitting here in the atmosphere, ionizing it, changing things. The other one is when we have plasma coming out. This is a snapshot of a shock wave in front of a so-called coronal mass ejection. It's got about an Earth mass of material moving about 1,000 kilometers a second outwards. And that, when it gets to the Earth and starts interacting with the magnetic field, can give rise to what we call space weather. So I'll talk about both of those things. I'll talk about them more than once, because much of this will perhaps not be obvious. It's not obvious to most physicists either, by the way. So that's what we'll be looking at. And this is the basic outline. First, I'm going to try and give you an overview of what space weather means. Basically, it's the influence of the sun and the plasma around the sun on Earth and human technology in particular. But it also relates to, for instance, variations of the atmosphere around the Earth over cosmic time. Talk then about so-called magnetic reconnection, production of X-rays, energetic particles, things like that, coronal mass ejections or CMEs, Then I'll be talking about CubeSats, of course, the Inspire-2 CubeSat and CUAVA-2, look at changes that they've seen associated with radiation effects, so energetic particles basically hitting the spacecraft, basically cutting current channels or causing so-called single event upsets in the computer memory. We'll look at changes there, we'll look at changes in the orbit of the spacecraft, a little bit on the electricity grid, and then talk about what we need in terms of better space weather predictions. And as we go, there'll be a mix of physics, even some experiments, although there are movies of those experiments. I won't do them in real time here. And there's also then pictures or movies to give the qualitative picture. So as I mentioned, what's space weather? It's all about the conditions in space that influence human technology and our environment. That environment can be near the Earth, so the atmosphere, things that happen on the Earth, such as time-varying magnetic fields that cause electric fields. Perhaps you won't know, well, most of us don't know, that one of the major sources of damage in computer chip manufacturing sites is in fact substantial variations in the magnetic field cause electric fields, and even over the tiny dimensions of a computer chip can give rise to large enough currents to actually cause damage. So actually, the people like, well, groups like Intel, Taiwan Semiconductor, etc., they care a lot about space weather and the associated changes in the magnetic field that induce effects down on Earth. And almost all of this activity is driven by the sun, either directly with X-rays, etc., or these coronal mass ejections, which have large changes in magnetic field associated with them, and that gives rise to a so-called electromagnetic pulse. Not the one associated with nuclear devices, but one just associated with a time-varying magnetic field that gives you a large electric field. And we'll be looking at those agencies moving out towards the Earth, and there's a shock wave, it turns out, in front of the Earth. I think probably all of you will have heard of the solar wind. That's just the hot ionized plasma or ionized gas, which is too hot to stay gravitationally bound to the sun, and instead moves outwards, going at about 400 kilometers a second. And that turns out to be fast enough to be supersonic. And just like a fast enough airplane, you get in front of it a bow wave or bow shock, and that's just what we're seeing here of the Earth's bow shock here associated with the magnetic field of the Earth that acts like a pylon in a river. So if you've got a bridge across a river with pylons down into the river, you know that the water doesn't flow through the pylons. Instead, gets funneled around the outside. And that's just what the shock wave here does. It takes the material from the solar wind, it slows it down, and it pushes it away outside of the magnetic field region controlled by Earth's magnetic field. But we get changes here, movement of that shock wave, movement of this plasma boundary here, the so-called magnetopause. We get plasma moving in down towards the poles, which we'll talk about a little bit more in a moment. And we see all sorts of other exciting effects. Now, too much detail here. I just want to make you, to just show you that there's all sorts of different regions around the Earth. They've got a complicated topology and connections, but they all relate to material either coming straight down towards the Earth via the cusps here and connection into from the solar wind, or it turns out quite a lot of it corresponds to an event called magnetic reconnection down here in the magnetotail, and plasma moving this way towards midnight and the dark side of the Earth. I will talk about the radiation belts a little bit. The radiation belts are energetic particles bouncing back and forth in the Earth's magnetic field, and as they go bouncing back and forth, they also drift around the Earth. So instead of just, if we're looking here at this one here, they don't just go bounce back and forth this way, they also drift around like that. Okay? And as they go, They actually carry a current that drives magnetic field fluctuations, which we'll be caring about a bit. So let's look at this to show a more qualitative view of space weather. So this is meant to be a representation of the sun, and we'll see an explosion fairly soon over here. It will actually be associated with magnetic field regions on the sun reconfiguring, and some of their magnetic energy gets put into motion, and that blob of plasma comes along, get reconnection here, those magnetic field lines break and come back in, and then they get pushed towards the center, and then we also get effects here with the energetic particles moving down and giving us the aurora. So let's show that again, because there's a lot of things happening. But this is the cartoon model of what's going on. So here again we have event on the sun, giving rise to some energization, blob of plasma moving along, probably about 1,000 kilometers a second, so really fast. Coming along here, it's got a magnetic field in it, reconnects here, magnetic field lines change. Some of that plasma can keep going in here, but much of it comes from the magnetotail, and you get the aurora tending to be on the night side of the Earth. And we'll talk about a little bit more about why in a while. But that's the picture, and I could talk for an hour, probably, about this diagram, but I'm going to try not to. Sorry, I'll be more direct. I will not speak about it for an hour. Instead, I'll just pick up on a few items that are probably interesting and relatively easy for us to understand. So one is energetic particles, whether they are galactic cosmic rays or just particles coming from the sun, so solar flare protons. They can hit, for instance, an astronaut, and the cells or the DNA in the astronaut, for instance, have particular connections between various atoms, for instance. Energetic particle coming along can basically push 2 or 3 of those out of the way, in fact, a lot more of them, break the connections. DNA then won't reproduce properly. You can have then eventually a cancer forming for that particular astronaut. And that's true, but to a much lesser extent for people down here in airplanes. The radiation dose there is very small in comparison, but it's not zero. Those energetic particles can also damage solar cells and electronics on spacecraft. And the idea is very simple. Just have a current channel like this, for instance. Energetic particle comes across, got lots of energy, it pushes the particles in the current channel out of the way, ionizes some of them, but mostly it just pushes them out the way, destroys the connection. So again, you would then have a solar cell that doesn't work, for instance. So those ones are relatively easy. What else might we talk about? We might talk about, for instance, changes in the magnetic field that induce electrical signals along power lines. Those electric fields can give rise to large currents. If those currents are too big, as they go through transformers, they'll cause the transformer to overheat and break. And that then stops us being able to transmit electrical power over the electrical grid, which is generally a bad thing. You also get currents induced in the Earth. We also get plasma bubbles, changes in the drag of satellites. And the idea here is at one level very simple. If we just have some extreme ultraviolet radiation or X-rays coming into the atmosphere, some of those are then absorbed, heat up the atmosphere. What happens when something's heated? It moves faster. Some of those particles are able to escape gravity or at least move up higher, and so the atmosphere puffs up. When the atmosphere puffs up, a spacecraft goes through it, it hits a few more of those molecules, slows down a little bit more. When it's too slow, it can't keep in its old orbit. In fact, has to move closer to the Earth and eventually spirals down and burns up. So those are the things we'll maybe focus on here. So why is space weather important? Here are two or three examples. I talked about them a very little bit yesterday, but the so-called Carrington event of 1859, as I said, in that case, there were no electrical power lines, but there were telegraph wires, which were long, and the change in magnetic field with time induced large electric fields, large currents. You got electric breakdown in the air between the wire and the ground, got little lightning flashes, forest fires, all sorts of good things, and people were actually able to run the telegraph wire or telegraph system with the batteries disconnected, just using power from the space weather event. But if that happened today, the prediction is that it would have taken out the American East Coast power grid. That power grid relies upon large transformers, which are made about 1 or 2 a year in a place in China. If you've now lost 100 of your major transformers and you can replace them at 1 or 2 a year, you're a major problem. Because anyone who's been to the east coast of the United States knows that in wintertime you want to have heating. Much of that is electrically driven. You want to have air conditioning in the summer. If you don't have that, we wouldn't be able to support the number of people that live there. The same is true for other places, Europe, China, etc. The electricity power grid underlies modern life. If you destroy it, we basically go back to the Stone Age. And the costs, even just with not selling the electricity, so ignoring the fact that suddenly people can't keep food for a week or two, and as you know, we do just-in-time manufacturing and delivery nowadays. So the supermarket basically has food that it sells today that arrived yesterday, mostly. Certainly the fresh food's that way. Real problem for society. And the costs, $1 trillion, maybe $10 trillion a year. You might say, well, surely that's okay. But the sort of cost for the Iraq war about 20 years ago was about $1 trillion a year. So it's a large amount of money, real problem. As I mentioned earlier, Earth missed a Carrington event much more recently, about 10 years ago. And the reason for that is just that the sun rotates basically once a month. And in this particular case, if you're the Earth, the sun had rotated, so the active region was on this side of the sun, and the coronal mass ejection and the flares and so on went off in that direction. 1 week earlier, it would have been pointing towards Earth, and we probably would have had very significant problems for our society. The other ones are not so important, but basically electricity grid, space assets, they basically underlie our modern life. And here's one just way of looking at it. Here's, can anyone tell me where Sydney is on this particular map?
Do you know where you can see the river on the top one? Where it comes in?
Yeah, so this particular, oh, I could have done it this way, couldn't I? You mean here? Yeah, that's a good guess. It's actually a trick question. Sydney's not on this map. which is a very naughty thing for me to do. Actually, Sydney's just down here. This is the Hawkesbury Estuary. This is Lake Macquarie here, and so on. So it's just a little bit north of Sydney. But these tracks are the sorts of things that a satellite will be able to observe. They might be taking spectra of the forest, for instance, there, or crops, working out whether things are ripe or not, whether it's too dry, and for that matter, just taking pictures of the environment here. You might do a spectroscopic analysis, maybe connected here, to work out whether you've got particular ores present on the surface. Is there more iron ore exposed here or there? Is it a place to go mining? Is there a flood? Many reasons why you might care. Here's perhaps an unusual one for you. Time goes this way on this graph. These are data from 2 NASA satellites. Basically do different, looking at different chemistry. So this one here is mostly about the the neutrals. I think it's neutral nitrous oxide in this particular case. And this is looking at the ions. And as time goes on, you see this nice diurnal variation. So this distance from here to here is 1 day. So you see the day-night variation. Here's another one. And then this one here gets disrupted. Turns out that there was a major solar event here. Large numbers of X-rays and extreme ultraviolet radiation changed the chemistry in the upper atmosphere here. So this is one example of how our atmosphere can get changed by space weather. Now, the atmosphere is pretty resilient. You can see that after a very little while, less than or equal to a day, we're back pretty much to normal. For here, not so true for here. So these variations can be subtle and important. And so people do wonder about how the Earth's atmosphere has evolved in response to solar events over the lifetime of the sun, which is about 5 billion years. There's also GPS, of course. We use it all the time. I'm going to use it later this evening to go to my oldest son's birthday party, because I don't know the location otherwise. But we do it all the time. And for instance, some of you will have come here by plane. It's really important to know whether your airplane is 10 meters above the ground, on the ground, or 10 meters underground when you're coming into land. And GPS is one of the ways to do that when you don't have good visuals, for instance. So those are just little examples, perhaps. So maybe I don't need to do the reminder here, and we'll instead just look at this. So what are we looking at here? Let's see, sorry. So what we're looking at here is data from the stereo spacecraft, looking from the sun, so close to the sun, basically to the Earth here. Here's Venus, and we're looking in white light, just looking at that light being scattered by protons and electrons in the solar wind. And you can see at a glance this outflowing plasma, and it's not nice and uniform, is it? Doesn't look the same in every location. You instead see striations, variations. It's brighter here than it is up here. That means it's denser in that location than the other. And the same sort of thing on the top. So you're just seeing directly the variability of the solar wind, even without a solar flare. So space weather is really something we should expect, and it's going to range from tiny little events to big ones. And it turns out even the tiny events have variations that we care about. And I think that's probably belaboring the point. Okay, so let's talk a little bit about some physics here, this sort of magnetic reconnection, which I will describe in terms of a sandwich or a burger analogy. So all of you know a bit about magnetic fields. You know, for instance, that you can generate a magnetic field by putting a current through a coil, and that drives a magnetic field. You know that you can have magnets, bar magnets, and you get a magnetic field associated with that. What happens when you bring two magnets with the same poles together? So North Pole here, bring them together. You know that they don't like being pushed together, right? But you also know that the magnetic field from this one is going to be directly opposite the magnetic field from this one. So right in the middle, we should have zero magnetic field. Now, it turns out that the magnetic field energy, or the energy in the magnetic field, goes as b squared, the square of the magnetic field. So it doesn't care about sign at all. So if I go from a situation where I've got some magnetic field here, and I push them together, somewhere in the middle, I've got zero magnetic field. Where's that energy gone? Where's the magnetic field energy gone? This is perhaps a more diagrammatic way of showing it. So here I've got a magnetic field mostly in this direction here, opposite direction here, bringing them together, pushing them in because the magnetic field's being carried by the plasma, which is moving inwards this way and this way. Right in the center, by symmetry, we'll have zero magnetic field. So what happens to that magnetic field energy? It's got to go somewhere. It goes into moving the plasma, gets squished out the side. So how many, I'm sure that none of you are as klutzy as I am. I have at times had a nice big burger. You know, it's a big one, so you've got to open your mouth wide, try to put your mouth around it, and isn't it amazing how always the contents squish out the side? And that's exactly what's happening here, the burger model. The plasma gets pushed out here, and it turns out that it gets pushed out with a characteristic speed, the so-called Alfvén speed. And I won't try and explain that more, but if someone has a question about it, I'll talk to you about it. Now, this model here of a solar flare is basically taking this and rotating it by 90 degrees. So rotating it, so taking this direction here, rotating it so it's now like that. So this region here, where I've got two magnetic field lines, one coming up here and then going down like that, they're anti-parallel here like this. And so what do we expect when we squish these two magnetic field lines, one going up like that, one going down, put them together, squish material out the top and the bottom. So I expect some material to go this way, some to go that way. The stuff that goes down here goes towards the sun. It in fact leads to so-called H-alpha flares or heating of the solar atmosphere. And the material that goes outwards becomes a coronal mass ejection. And that has a characteristic speed, so-called Alfvén speed, and not all of the energy, it turns out, goes into outflow. Some of it goes into heating and acceleration of particles. And so this is an example of that, and I'll show the movies in a moment. This is from SDO as well. So here's the large-scale picture, and we'll be looking at this active region here with the magnetic field loops. So like a bar magnet in many ways, you get the nice loops going around. And then this is a close-up, and then this is another close-up where we'll reverse back and forth. And what we're wanting to see is outflow events. We'll also see regions which become brighter, and that's because of heating and increased density, mostly heating though. And what we might expect is that since we're looking in extreme ultraviolet light here at 171 angstroms, these basically are almost like X-rays. And what we see here is the AIA, so the brightness here from a given region just in here, varying with time. See all these nice events. We also see X-rays at different times, and it turns out radio waves, which is one of my loves since I was a PhD student. So let's just see whether we can get this to work. So I think what we can see, you're seeing some of the outflow here. Is it being obvious over here? Let's try it again. This is a faster computer than my laptop. So here's one of the outflows. You can see here the outflows going quickly, and here's another event. We see the outflows going out. So this is all believed to be magnetic reconnection, and so you have the EUV radiation here associated with the reconnection here, the X-ray events, and the radio events sort of lining up. So really want to just emphasize the reconnection and the outflow here. Come on. So that's one example. Here's one, it's a much older one, about the time, well, actually earlier than you were born, all of you, which I apologize for. We've gone into a particular active region. We see this snow every so often. The red contours correspond to X-rays being produced, locations, and the blue are gamma rays. And you notice these evolution of these magnetic field lines, heating often up the top, which is what that model that I just showed you gives, but also some heating down at the bottom. Let's just do that again. So going into a particular active region here. Oh, my thing doesn't work that way. sorry, I've gone the wrong way. Come on. So the X-rays here, sort of out. Keep forgetting that I can't do that. All of this snow here, variations here. These are energetic particles coming down from reconnection regions up higher. All sorts of variations. So what do you think the white dots are? Radiation, which means in this case perhaps energetic particles. So it's energetic particles. So if we were up there in space, we had the right eyes, we'd be able to see individual particles hitting our eyes and giving us flashes. In fact, actually the astronauts quite often see lightning flashes in their eyes as well, with energetic particles coming through their eyes, giving them Cherenkov radiation. They see a flash of light with each of them. If you're close enough to a lightning flash on Earth, you can see exactly the same thing. I don't recommend that you try it. Yep, so that's the energetic particles with, well, okay, the snow. So you see all sorts of activity, and this drives the space weather at Earth. Come on, let's go further. So let's talk about the photoelectric effect. So this is an experiment here. Maybe I'll stop for a moment. Have any of you, well, this is an experiment for the photoelectric effect, which is an effect of light with a suitable frequency hitting a metal in particular, giving enough energy to the metal atoms to be able, and actually electrons in particular, to be able to kick the electron off and change the charge state of the metal itself. And the way that you demonstrate it is via an electroscope, which you can just see here. There's a piece of metal on the top, basically just a metal plate connected down to two pieces of foil, which are separatable. And you can see at the moment the two bits of foil are separated. You can see the shadow here, and that's because there's a charge being put on that. And so the charges, which are electrons here, don't want to be together, so they push each other, they push themselves apart as far as possible, and that then opens up the two foils there. And so this is something actually Einstein got the Nobel Prize for. Photoelectric effect, and basically it's shining light onto the metal and then giving enough energy for some of those electrons to be able to escape from the metal. When they do that, they change the charge. And so let's just look at that. And in this particular case, he's now put the light on and it's discharged. So he's going to do it again. So charging up. See the charge there with the separation of the foils, with the shadow. And then he's going to put it over again, but now with a perspex plate, so that the ultraviolet light can't get through. Do it again. And try ordinary light, and it will do nothing, because ordinary light, the visible light, doesn't have enough energy to kick the electrons off. And that was one of, you probably know that this is one of the experiments that basically proved the necessity of a quantum picture of light, of the universe, that light came in bundles or photons with energy. That energy is equal to h times the frequency. And if you then just conserve energy, you can prove that you need light of above a certain frequency to be able to get this effect to work. So this is the photoelectric effect, and you can write it in a so-called Feynman diagram. So how many of you have seen a Feynman diagram before? Okay, quite a number. I'm impressed. So this is one way of looking at a Feynman diagram. So time going up this way, our particular way of looking at things. We've got an electron here meeting the photon hitting the electron, and then just the electron going. It's got enough energy now to get out. So that's one way of doing it. Electron plus photon gives you a higher energy electron. But can you go the other way? Can you take a high energy electron and in some sense move time backwards, give out at the end a photon plus an electron with lower energy? And that's really how we get the X-rays that we were just looking at. And one way of showing that is you can get an electron beam, you basically target some metal here, molybdenum for instance, and you can get X-rays emitted, and then you can look at the X-ray spectrum, and it has a minimum frequency, or sorry, other way around, maximum frequency, minimum wavelength corresponding to the maximum energy of the electrons. And so this is how the X-rays that I was just showing you get produced. Energetic particles getting close to other ones, being moved by the electric charges and giving up photons. So a little bit of Einstein doesn't go, is a good thing. Okay, so what about coronal mass ejections? I'm going to show this quickly and then go back. So again, you see the energetic particles, but let's go backwards in time. Come on. On my laptop, I can slow this down. What I wanted to do was show this. I can't do it this way. Oh, I can do it this way. Okay. Okay, so if we go out in time slowly, you can now see the coronal mass ejection very close to the sun, further away, etc. Okay. Turns out that those energetic particles here are associated with a shock wave that's in front of this coronal mass ejection. Come on. So just upstream here, you get a shock wave, just like Earth's bow shock. I thought I should show you some examples of radiation actually leaving visible trails. Have any of you seen a cloud chamber before? Okay, lots of you. Impressive. That was an experiment I could have produced here, but it's finicky. And so I thought it was better to just describe it. And so here, with the way in which it's done here in the school, but elsewhere as well, basically have a container. We have quite a bit of water vapor in here. It's meant to be super saturated, so that when you have an energetic particle going through it, it can give energy up to the little water droplets in the air. And when it does so, it gives rise to a trail. And so you can see some of these trails. Sorry, I want to show them here. Here's one trail here. Oh, sorry, it doesn't work that way. One trail here, some other ones. These are energetic particles moving out, giving rise to ionization trails, condensation, because they're giving up energy to the water and giving up energy, and then you get this water droplets and a stream of them. And here's another view of it, just looking at where you might have a needle of radium sticking down into the region here, and you get these energetic alpha particles moving out. So alphas, of course, are just helium nuclei. And then you also get electrons as well, which tend to have these non-straight, let's put it that way, trails. And the reason is just because they have low mass. So if there's a collision, they get moved rather than the atom being moved. So that's one way of visualizing the trails associated with radiation. Don't know quite why I went that way. Sorry, going the wrong way. So here's one example of radiation damage. It's a very old one, but it's quite nice and clear. It's just looking at various voltages and currents on solar cells on a spacecraft in space. And you can see here that in a particular time, August of 1972, there was a big solar event, and you got substantial changes in the characteristics of your solar cell. And this is due to the current channels being broken. But not all of them, just some. And that's because for each case, you need an energetic particle to actually go through, hit a current channel, break it, but there are other current channels. Do you have enough radiation going through to break all of the current channels or not? It's statistical, because there are, space is large, so the chances of a particle going through just where it needs to is small. So it can be very statistical and difficult to predict. So we know all about CubeSats already. Don't need to go over them. Don't probably need to talk about INSPIRE going into space. Let's just talk about this, which I did show you briefly yesterday. These are the data from INSPIRE 2, June to October of 2017. What do we have here? We've got energetic particles observed in the solar wind. This is the first solar event seen for 1.5 years or so. You can see a big event here, little one here, a bigger one later on. What we have up the top is fluctuations in the magnetic field seen in the auroral zones of Earth. And that's just because of energetic electrons moving down, sometimes giving aurora, but causing ionization changes, currents, magnetic fields. And you can see lots of variability there. And what we have here is the current seen by, or reported by INSPIRE, and the temperature. And here we have, pretty good behavior. And then suddenly from this point here in late July through to September, nothing at all. The spacecraft went dead for a while. And you notice that it was not at the peak of the radiation event here. It was, towards the end of a pretty small bit. So radiation damage is quite statistical. It's difficult to predict. Similarly, we survived unscathed through this bigger event here. Dash, sorry. Keep on forgetting. Yes. So big event here, small, big. The only event here that was important from the point of view of INSPIRE was the radiation damage here. So it's, difficult to predict when that's going to occur. Didn't occur at the maxima. This bigger event didn't give rise to further radiation damage, although you notice here that our temperature for the communications board was 0 afterwards, indicating damage. So this is one example of damage to a spacecraft due to a space weather event. Or I should put it differently, almost certainly due to a space weather event. So I showed you a bit of this last time as well. So the picture again, we're looking at Earth's magnetic field here. The purple is the undisturbed field lines here. And then we've got some connecting in from the solar wind through the cusp and through the magnetotail here. This is the auroral zone, the radiation belts, particles bouncing back and forth and drifting around the Earth. And so we would expect significant radiation counts near the poles. And if we look in the radiation counts here, near the poles, near the auroral zone, for instance, substantial amount of radiation, but you notice a pretty low level in general, even lower level near the equator, and then back up. Again, some events here, and this is the southern Atlantic anomaly that we talked about last time. That's this weak region in Earth's magnetic field in which some of the, well, a lot of the radiation or the energetic particles come down into the atmosphere. And you notice that this is, about a factor of 3 more intense than the other one. Here's the southern Atlantic anomaly. So is this usual? This was the 10th of April, not April Fool's Day. 1st of March, so about a month before. You notice almost nothing over the poles. Pretty big event here over the southern Atlantic anomaly. Again, sort of locations about right for the southern Atlantic anomaly. Some events up here. You can see them here and here towards the auroral zones. And So the space weather varies with time. And here's just a direct comparison between those two events, 1st of March and the 10th of April. You see the level of the radiation of the southern Atlantic anomalies, pretty close, better, but big differences here over the poles. So sort of interesting that you can see nice space weather events here with a CubeSat, for instance, and over time,
That's dismissive. Like, thank goodness for that. Like, that's awesome stuff. We have time for some
and
questions.
look at changes in the southern Atlantic anomaly with time. I said I'd talk I thought I'd give you a movie of just changes in current or electric field associated with time-varying magnetic field. So over here we have just a coil, so electrical circuit, just a coil. We're going to put a magnet into that. As we move it in or out, we're going to give rise to a current here, and so show Faraday's effect, the development of an electromotive force. This really is quite a quick computer compared with mine. So as you change the magnetic field, you get an effect. When it's stationary, you don't. Again, move it out. And so here is an example. It's an example with an electrical substation here in Australia from the Bureau of Meteorology. A standard current here, then a space weather event, and you see a change in the current by close to a factor of 2 from here to here. That sort of factor of factor of 2 didn't hurt this transformer. Bigger one might. And transformers are kind of expensive to replace. You don't want to do it often. So that's an example there. And whoops, wrong way. Come on. I thought I'd talk a little bit about orbits of spacecraft. So I think you probably know that you can describe an orbit as an ellipse, for instance. An ellipse has a number of parameters that you might use to describe it. One of them is the semi-major axis. So officially, the distance between distance between the center here and one focus. Yep, sorry. Between the focus and the center here. But that's also equal to half of the sum of the apogee and the perigee distances. So if you look at the maximum and minimum distances that you get, take the average of those, you get the semi-major axis. And that's the quantity A that I will talk about. And I'll particularly talk about dA by dt, so the time rate of change of that altitude. There's also various other things, the inclination angle of your orbital plane to some reference plane. So normally that would be the ecliptic plane, or it might be the Earth's equatorial plane, depending on what orbit you're talking about. You've got the eccentricity, which is how much that ellipse is squished. So how far is it away from a circle? And then various other ones that I'm not going to bother you about. But one other that's important is the so-called B star, which is a drag term. So it's a representation, basically a fudge parameter, for those of you who like the Greek, for other things we couldn't take into account with our simple model of an ellipse, or rather time variations in the ellipse. So these are data from CUAVA 1. The apogee or the altitude here, the red line is that quantity, and you can see that it varies, normally pretty smoothly, and then there are sudden variations. There's a bit of a variation here, and if you look at dA by dt, the time derivative, you can see a big effect here, just in correspondence with the slight change in slope there. Same sort of thing throughout here. It's much easier to look at dA by dt rather than A as a function of t. That derivative picks out features beautifully for us. And why do I care? It's because if I compare that dA by dt, which is in this case the red here, the slope that I had before, and here we have F10.7, which is a measure of radio waves from the sun from these solar active regions. So it's a representation of solar activity. So when it's big, we've got lots of solar activity. When it's small, we've got little. And what you maybe can see, just at a glance, is that where we have a peak in F10.7, we have a minimum in dA by dt. Corresponds to maximum change in dA by dt, maximum acceleration earthwards, or drag. And you can see that pattern nicely showing up throughout this. You could also look at the drag parameter B star with another representation of solar activity. This is radiation in magnesium 2 lines, it turns out. The details don't matter. What does matter is that where you see a peak in one, you see a peak in the other. You can see that they're beautifully correlated. So what does that mean? It means that changes in the solar radiation, extreme ultraviolet light, and things to do with solar activity, or active regions, change the orbit of the satellite around the Earth beautifully. What about CUAVA 2? Situation's interestingly a bit different. So here we have the altitude as a function of time for CUAVA 2 in red and Waratah seed in blue. And what you might notice here, yes, there's dA by dt here and a big event here, corresponds to this sudden change here. Turns out to be a 300-meter drop in the spacecraft, boom, in less than a day, due to a space weather event. What is it correlated with? Well, with B star, the drag, you can see that dA by dt and B star are nicely correlated like you might hope. You can also look at the eccentricity, nice and smooth changes, but it's very, very close values to 0. I've lost the decimal point here, but it should be here, 0.0010. So these are really close to a perfect circle for this orbit. And here's the inclination angle, nice, slowly varying things. But what about the changes with space weather? So F10.7 centimeters, which you might remember was well correlated for CUAVA 1, do you see a correlation there? What might I be looking for? I might be looking to see if there's a peak in F10.7 that lines up with this change dA by dt corresponding to this sudden 300-meter drop. What you can see is that there's no peak in F10.7. Not what we saw for CUAVA 1. But if you look at a representation of the auroral changes in magnetic field, Kp, there is an event here that lines up beautifully. If you look at DST, which is a measure of the number of the current in energetic particles in the ring going around the Earth, you can also see a nice peak there. So for CUAVA 2, which is in space now, about 5 years after INSPIRE, you can see a very different behavior. In particular, solar activity directly is not very important, but local geomagnetic activity is. You can also notice that behavior for CUAVA 2 and Waratah seed, is measurably different. I mean, these guys are a kilometer apart, and they were injected into space about 1 minute apart. So the initial orbit was very close. So why do you think there might be a difference in the behavior for CUAVA 1 and CUAVA 2? One of them well correlated with directly solar-driven activity, and one not. Do you know about changes in the activity of the sun with time? Well, there is a solar activity cycle, which is 11 years approximately. So what I have in this montage is the view of the sun on a given day of 10 different years sequentially, going from close to solar maximum, when we've got nice bright X-rays and activity, nice puffed out solar atmosphere, it looks hot, more plasma, etc., more of these bright intensifications. And at solar minimum, you notice that it's almost dark. You almost can't see it. And this is a direct demonstration that the activity on the sun changes markedly with time. 11-year cycle, so-called dynamo cycle, which we don't fully understand. CUAVA 1, this should say Inspire 2, was launched about here. We in CUAVA 2 and us today are here, near solar maximum. So if you have a big event here, is it going to be very different to what's the background at that time? Probably not. It's probably going to be just a little difference, because I've already got lots of X-rays and ultraviolet light, got lots of heating of the atmosphere, so it's going to be puffed up a lot. So really, the direct solar driving probably doesn't matter in this particular case. But here, even a modest change might give you big differences. And I think that is the explanation of the difference. That Inspire 2 was near solar minimum here, so a significant change in X-rays made a big change in the heating of the atmosphere and its puffing up and the drag. But at this time here, CUAVA 2, just recently, we're already puffed up about as far as we can go in Earth's atmosphere. Some more X-rays, not really going to make much of a difference. And so then we've got other things that are important, the geomagnetic effects, due to the energetic particles coming down into the polar regions, heating up the atmosphere there and causing effects. So I think that's what's going on, but I'd be happy to discuss it more with anyone. And there's all sorts of other things we could talk about here. I just put this slide in because we don't know how to predict space weather very well. We're at the stage of space weather forecasting that people were at 40, 50, 60 years ago for ordinary weather, where you'd look outside and you'd say, clouds in the sky, it's going to be cloudy. Temperature's about this, probably going to be just like it was yesterday. Not very sophisticated, not very accurate. Modern satellite data has changed that picture entirely. Now we can predict the weather at a sort of 80, 90% accuracy 3 or 4 days in advance in Australia. Even better in the Northern Hemisphere. We can't do that for space weather. Basically, we can look and see a solar active region and say, looks intense, big magnetic fields. Maybe there'll be a big storm or a space weather event, but I don't know whether it's going to be tomorrow or 2 days from now or a week or never. I don't know whether that coronal mass ejection that might be produced is going to hit the Earth or not. Or put another way, a bit more accurately, I don't know whether it's going to occur in this 12-hour period or the next 12-hour period or the one after that. And if I don't know that, the electricity people are not going to shut off their power lines and stop selling electricity, because the economic loss with not selling electricity is not worth it to them to safeguard the electrical power system. All sorts of other good things, GPS dropouts, the electricity grids, energetic particles. We can't predict energetic particles very well. You know, it's improving day by day, but it's not very good. So for instance, we'd have a really hard time justifying sending some astronauts to Mars, because we can't predict how many big events are going to occur and whether people will get a lethal dose of radiation. We can probably do that for people going to the moon accurately enough. But if you want to put people on the moon, Mars, this is the sort of thing we've got to be able to do. So it's an exciting time for those who want to do space weather research, because we know a lot, but we also know that we don't know an awful lot, and it's things that are predictable in principle, in my opinion at least. So space weather, the conclusions, it's conditions in space that affect human systems and our environment. That's our environment on Earth, down here at the ground, in the atmosphere if we're flying, if we're in space nearby, our environment, perhaps throughout the solar system, including Mars, for instance, and the moon. It's mostly driven by solar activity. Big events are possible. I didn't say this yet, but other stars that are believed to be very similar to our sun, our star, sometimes have flares that are hundreds or thousands times more intense in white light and X-rays than our sun. If we got a solar event that's 100 or 1,000 times bigger than the Carrington event, what does it mean? It probably means the coronal mass ejection's 10 times faster. Probably means the magnetic field change is at least 10 times faster. Almost certainly we have major, major problems for our electricity grid. And yet we can't predict it accurately enough, and we need to be able to do it. And yes, CubeSats, in my opinion, are really useful. A step for us to go. Hopefully something that some of you at least will be interested in. And even if you say, oh, CubeSats, they're too small, well, go bigger, right? But have a purpose, a reason for going bigger. And do something useful once you get into space. I personally think the ionospheric or near-Earth space weather is a major target. Some of you will know of the American Global Dynamics constellation, which is almost certainly going to be canceled by the current president. Even NASA wanted to cancel it last time, despite the Academy of Science saying it was their #1 priority. That's something that we and people from all of the nations here could do usefully, and do it at a tiny fraction of the $1 billion cost that's predicted. But we can do really useful space weather, even with small CubeSats, and that's including radiation, it's orbital variations. Some of you know that Elon Musk's or Starlink's constellation has 5,000 odd satellites in orbit. Huge number of trajectory corrections every day, even normally. When you get a big space weather event like the one that caused my 300-meter drop, the number of trajectory corrections goes up by a factor of 10. It becomes increasingly difficult to be able to predict where your satellite's going to be and whether it's going to hit something. And those are things that are very practical, because none of us want the Kessler syndrome, and none of us, for instance, want to be without our internet or wireless communications if we're relying upon those. So enough from me. Thank you. Onwards and upwards, and I'd love to answer any questions you have.
Yes.